In this video, we're going to talk about heaps and priority queues, which are a data structure that we can implement very easily using heaps. So the definition of a heap, and specifically we'll talk about a MinHeap here, is it's a complete binary tree, and each node in that binary tree holds an element that's less than the element that each of its children would hold. So there's an ordering where the smaller elements are always on top. You would never have a case where you would have a parent that had a larger element than a child. The child would always have the larger element. And it's also complete, meaning that it's full all the way through the bottom level, and the bottom level we fill from left to right. So here's an example of a heap, and you'll notice we have 2, which is the smallest element in the heap at the top. Its children are 4 and 5, both of which are smaller than 2. 4 has as its children 6 and 15, both of which are smaller than 4, and 5 has as its children 7 and 11, both of which are smaller than 5. Now you'll notice the ordering is top to bottom. There isn't any left to right ordering. So while 4 is less than 5, that's just the way it worked out. Here you can see that we have 15, which is the largest element in the heap. It's actually in the left subtree. So that's one of the things that distinguishes it from a binary search tree. So suppose we want to add an element to the heap. And again, this is a MinHeap. So here we have the element 3. The first thing that's going to happen is we need to add a node so that we still have a complete tree. So the only place we have where we can add this particular node would be here as the left child of 6. So let's create that node. You'll notice if we put 3 here, this isn't a valid heap. If we put 3 here, that violates the heap constraint here because 3 is smaller than 6. Let's swap the 3 and the 6. But again, you'll see that we're violating another constraint between the 3 and the 4. So we're going to swap the 3 and the 4. And now we have a heap that satisfies all the constraints. As we add more nodes to the heap, that's what we'll keep doing. We'll add the node in the place that makes the tree still complete, and then we'll swap parent and child all the way to the root if necessary to maintain the ordering constraint. Now to remove an element from the heap, we're always going to remove the top element because that's going to be the smallest, or in the case of a max heap, it would be the largest element. It's the one that we've set up the heap to maintain an easy access to. So here, if we're going to remove the minimum element, so we'll keep this object out here and we'll return that to the caller. And then we're going to find the last node we added. Now in this case, it would be the node with 11 in it. So we're going to delete that particular node. And then we're going to move 11 to the root. We're going to swap those values. Now, one thing that should jump right out at you is now we have an invalid heap because the larger element has smaller children. To resolve this, we're going to do something similar to what we did with add, only in the reverse direction. So now the smaller of my 2 children is 4. So I'm going to swap the 11 and the 4. But then I need to check to see that now we're still violating a constraint here. 11 is smaller than 15, but it's bigger than 6, so that violates the constraint. So we need to switch those 2 elements as well. And once we do that, we have a heap that satisfies all the properties, and we can return our 2 to the caller of the remove min function. Heaps are very useful in implementing priority queues. So a priority queue is a data structure that has not one, but several different queues inside of it. And so let's suppose that this is an example where we have some queues, and you can see we have 2, 4, and 14 in the bottom queue, 3, 5, and 18 in the top queue, and 1 in the red queue. In this particular case, red is higher priority, yellow is medium priority, green is low priority. And each of these represents the waiting time. So 18 has been waiting the longest, followed by 14. And then we have a 5-minute, 4-minute, 2-minute, 3-minute wait. And then this high priority item has only been waiting 1 minute. So with a priority queue, we don't just consider how long something's been waiting, we also consider its priority. Higher priority items always have preference. So in this case, the next item that would be removed from the queue would be the 1. Then it would be the 18, because that's the next waiting element. Now, once we remove 1 and 18, you'll notice we'll have 5 and 14. And even though 14 has been waiting longer, 5 would have priority since it has a higher priority value. So we can use heaps to implement this particular data structure fairly straightforwardly. Now the way we're going to do this with a heap is we're going to put each element in a wrapper class that includes the element itself and the priority. So we'll put 1 in a high priority element, and then 3, 5, and 18 would go in medium priority elements. And keep in mind that the number here is the waiting time. So this will actually be a max heap based on waiting time. However, since this is a priority queue, the priority takes precedence over the waiting time. So there's two components to the comparison we do for each of these elements. First off, what's the value of the priority? Higher priority items are always going to have precedence over lower priority items. Then the next thing will be the waiting time. So we have higher priority elements like 1. We have medium priority elements 3, 5, and 18. And then the lower priority 2, 4, and 14. So let's build the heap. So the highest priority element is going to be 1. So that's going to be the max element. It'll be the root of our heap. Then we have some medium priority elements. 18 would take precedence over the others because it has the higher waiting time. And then 5 would be next. Although it doesn't really matter if we put 3 or 5 here, because all that matters is that something lower priority than 1. And so we can put the 5 here, and then the green ones would all go on the last row or the last level because they have lower priority, and it doesn't really matter what order they're in. If we had it in this order, it would still be perfectly valid because, again, the key is the things we're going to remove first from the priority queue in this case should always come first. And then we can draw our lines between. So that's what the priority queue implemented using a heap would look like. We would pull 1 off first, then 18. Now you notice that once 18 has been pulled off, 5 would be next. And so 5, as we move things up and keep this complete, we would eventually make sure that 5 comes before 3. And then we would continue removing things, but we would get the correct order. And if we added something higher priority, notice it would always go to the top because we only have the one high priority element. So if we added another high priority element here, then it would swap here with 5. It would swap with 18, again, lower priority. So the 18 would go below even though it had a longer wait time.